Well, thank you for introducing me. Good afternoon, everyone. And I'd like to thank the organizers of this workshop for inviting me and my colleague, Eric Camret, who really is the father of the CWIPI library, but he apologizes because he couldn't be available for this workshop. So I'm going to be presenting the CWIPI library. I'm a research engineer at UNERA. I've been working there for the last 2 years as a research engineer, and so I'm gonna present to you the CWIPI library. So first, I'll start with presenting the main features of the CWIPI library. Then I'll show you some examples of the typical applications of this library. And I'll conclude by presenting what we are currently working on and what we plan to work on in the next few years. So CWIPI has a lot of similarities with the other libraries that have been presented earlier by the lecturers. So like Precise, PLE, and MUI, it's a library. It's also open source under LGPL license. So it targets coupling of codes in a massively parallel distributed environment. And so as Yvan Fournier said earlier, the development of CWIPI started back in 2009. So at this time, it was only Eric Camret that was working on this. And it was based on the BFT and FVM libraries, which have now evolved into PLE. So you will see that there are a lot of similarities in the philosophy of CWIPI and PLE. It's written in C++, but has wrapping for C, Fortran, and Python. And I've shown the link where you can download it. So the website is currently only in French and with quite little documentation, but we intend to correct that in the next coming year. So who developed CWIPI? We are two at UNERA. There's Eric and I. And we also have colleagues at CERFACS who help us developing CWIPI, but none of us actually is working full-time on CWIPI because we have other projects. So there are two ways to operate CWIPI. First, you can call it directly from the coupled applications. So I'll show you next an example of how it can be instrumented. This way, we only support MPI communications, but there is another way. The user can call CWIPI via the OpenPalm tool, which is developed at CERFACS, and which enables the user to use a graphical interface to design its coupling schemes. And this way, it supports MPI as well as TCP/IP communications. And as you can see, both ways are actually used by engineers as well as researchers, and primarily in aerospace domain. So CWIPI actually requires that the coupled codes are run in the same MPI environment. And if the codes are themselves parallel, they all must be compiled with the same MPI implementation. So this is currently a constraint that we are working to eliminate. I'll show you. I'll talk more about it later. So at initialization, CWIPI creates an internal communicator for each of the couple codes. And then for each coupling defined by the user, CWIPI creates an intercommunicator between the processes of the couple codes. This is quite similar to what has been presented earlier by Yvon. So the goal is that from the user's point of view, the inter-application communications are completely transparent. And so even if the applications are themselves parallel. So CWIPI does not provide any predefined coupling scheme, but rather we let the user design their own coupling schemes using what we call control parameters. So these parameters are actually global variables that are shared and synchronized between the couple codes. So there is no default control parameter, but it's quite easy to define the one the user needs. So, for example, you could use a global parameter to keep track of the simulation time. CWIPI, so as you know, the coupling between the codes takes place at the interface between the meshes of both coupled applications. And CWIPI supports interfaces of any dimension. So you can have line, surface, or volumetric coupling interfaces. And those interfaces and meshes can have any type of elements, even polygons and generalized polyhedra. And the meshes on both sides of the interface do not have to match. So you can this way you can couple using a surface immersed in a volume or overlapping domains. And when it comes to the communications, the CWIPI builds a point-to-point communication graph based on the location of the target degrees of freedom. And that way we can reduce the amount of communication to the strict minimum. And this communication graph is then used to exchange interpolated fields using either blocking or non-blocking point-to-point MPI communications. CWIPI can also handle high-order interface meshes with either straight or curved mesh elements of any standard type. So again, one-dimensional, two-dimensional, or three-dimensional high-order elements. And because there really is no standard way of defining such high-order elements, CWIPI provides the user with a way of specifying how the nodes are numbered for each type of element. And as shown here, this is done by providing an array of coordinates for each node, and those coordinates are given in the parametric space of the element. And that's kind of a more advanced use, but the user can also choose to use different orders for the geometry and the numerical method. So the standard coupling workflow is as follows. So the target degrees of freedom need to be localized in the source mesh. So this is done by locating in the first level. It's we seek the partition in which the target point lie in the coupled domain. Then in which element this point lies, and we then compute in that element the mean value coordinates of the point. So actually, currently the CWIPI uses the same localization algorithms as the one in the FVM library. So it's very similar to the one Yvon described earlier. By default, the degrees of freedom of both source and target meshes can be located either at the nodes or at the cell centers. So if and CWIPI comes with a prepackaged default interpolation method. So if the degrees of freedom are located at the nodes, then the default interpolation method is as the same order on the same order as the elements in which the points are located. And if the degrees of freedom are at cell centers for finite volume methods, for example, then it's simply the interpolation is simply a nearest neighbor interpolation. So once you have interpolated your source field at target points, we can exchange these interpolated fields. And CWIPI also provides functions for exporting this interpolated field. I believe it's in the Insight Gold format. So to illustrate this workflow, this is a quite basic example of coupling between two codes, one written in Fortran in the left and one written in C. As you can see, the API is quite similar for both languages. So if we look at the different steps, so both codes start by initializing the MPI communicators by specifying each one specifies its name, its application name. Then both codes create a coupling by specifying the name of the coupled application. Then they each pass their interface mesh to CWIPI. Then we can localize the target degrees of freedom from in the coupled mesh. So next, we show an example of how you can use the control parameters to design a customized coupling scheme. So here, the C code defines a specific number of iterations. This is quite a dummy example, but and then in order for the Fortran code to have a coherent value for this parameter, we need both codes need to synchronize the value of this control parameter. Then this control parameter is used to loop over some exchanges. So here we have a non-blocking communication, and so the CWIPI ISEND method mimics the MPI ISEND non-blocking point-to-point communication, but it really is a single a single call to CWIPI ISEND actually represents all the point-to-point communications from the current process to its coupled processes. And once the exchange have terminated, both code can delete the coupling objects and finally end the communications. As I said, CWIPI also has a Python interface, which is dependent on a few quite standard modules. And then again, the API is pretty much the same and quite straightforward. CWIPI also offers more advanced features, especially for when using high order meshes. So for example, the user is able to define custom target points. So if you don't want to use nodes, well, mesh nodes and or cell centers, or if you have high order mesh elements with unevenly spaced quadrature points, such as Gauss-Lobato or whatever, CWIPI provides a set of functions to customize your query points for interpolation. And CWIPI also CWIPI has two default interpolations, but you can also write your own interpolation method, which can use the data provided by CWIPI, which is the result of the localization algorithm. And this way you can use, you can potentially use your specific internal data structures of your own code, as well as your the specific basis functions that you use in your code. So the user can use a customized interpolation method instead of the default one, and this is done using callbacks. So this allows for more advanced users great flexibility in developing high order or generic coupling schemes. And CWIPI is mainly designed to address, as I said, massively parallel coupling applications. So performance is obviously the focus. So here we have a strong scalability study, which was made now about 6 years ago, but it's still okay. So it is a typical turbo machine applications using the AVBP solver. So here we couple two instances of AVBP solver. I'll show you later an example which is quite similar to this one, but even bigger. So here we have in total about 800 million elements, and computations were run on up to 64,000 cores on Titan, and the coupling interface is distributed across about 5,000 cores on each side. So here we see that the point localization algorithms show quite nice scalability, and the exchange part is quite negligible compared to the point localization. But when we use up to 10,000 of cores, we see that the cost of communications start to slightly increase. So this might be an issue, but still, the step that is the most significant, which is localization, behaves quite nicely in this range of number of cores. So now I'd like to show you some nice examples of applications which are quite diverse, and I think illustrates quite nicely the range of what you can do with SWIPI. I hope you can see all the nice animations. So this first example is the coupling between the CFD solver CEDR, which is developed at Onera, and computational aeroacoustics code space, which is also developed at Onera. So on one side, CEDR solves the Navier-Stokes equations using LES method, and the other domain, space, solves Euler's equation using DG method with high order, I believe it's up to 4th order. So here the coupling interface is drawn in red dashed line here. This is a surface coupling. I believe in this case the mesh match on both sides, so it's this is a matching interface. And similar calculation, not this one, but similar calculations have been performed using curved elements in the aeroacoustics domain. Next, we have an aero-mechanical coupling of so here we have a solid rocket booster. So this part of the launcher, and here we study the fluid flow inside the combustion chamber, and we have solid grain propellant which is burning and converting to gas. So as it's burning, the fluid domain is growing, and here SWIPI has been used to study the dynamic coupling between the grain regression and the fluid flow. And here we have I believe it's the temperature field inside the chamber. Next, we have a nice fluid structure interaction. So this computation has been run using the Yale solver, both for the fluid part using an ALE method, and and also for the structural mechanics. Here, there's also a dynamic mesh adaptation. So I'm not sure you can see, but the mesh is evolving. They used the MMG library for mesh adaptation. And quite interestingly enough, the authors of this study did not contact us in any way, so they did manage to implement this coupling without any help from us. So it shows that SWIPI is quite, despite the lack of documentation, SWIPI must be quite easy to implement. And last but not least, we have a very interesting turbo machine calculation. So this is one of the first full engine calculations. This calculation was done at CERFACS. So there's much to say about this calculation. Here we have 3 instances of AVBP, which are coupled using 2 instances of SWIPI. So there is a first rotating domain for the first part of the rotor. Then I believe it's this part is another domain, and finally there is a third rotating domain here. So for both coupling interfaces, we have a volume coupling interface that's shown here, which is also rotating. So here we have to recompute the localization at each step to take into account this relative motion. And this is quite a big mesh, because there is about 2 billion elements in the whole domain. So I believe this example demonstrates the need for both efficient geometric algorithms for the computing localization, but also shows that no, I believe that's all. I'm sorry. So yeah, this calculation was performed last year, I believe, yeah, and it demonstrates that CWIPI can be used in high performance computation context. So now to conclude, I'd like to talk about what we are currently working on with Eric, and about the major new version that we are preparing. So first, as I said, currently the CWIPI uses the same localization algorithm as FVM. So it's pretty much the same as the one Yvon described earlier. And we are working on improving this algorithm. So first, there is a major constraint currently on the distribution of the partitions of both coupled codes on the processes. Currently, I believe Yvon showed this as well. We cannot have different codes running on the same processes. So we intend to, we are currently working on removing this constraint. For now, the new geometric localization algorithm we have developed has removed completely this constraint. And we also have improved the performance of the algorithm by using fully parallel distributed octree data structure, which is based on the same principle again as what Yvon Fournier described earlier. And the issue of dynamic load balancing has been raised quite a few times today. And it is crucial for high performance computing. So the new algorithm we have written is fully balanced and dynamically balanced. So now all processes are involved, and this is quite important, as shown on the diagram on the right, which shows that in a typical turbo machine calculation, actually very few processes are involved in the coupling, and this might be a bottleneck in applications such as the one I showed just earlier. So to illustrate what I just said, though here we studied the performance of our new geometric algorithm in a quite straightforward case of surface coupling, such as the one described just here. So we see that we observe an acceleration of up to a factor of 5 compared to the current implementation. So this is quite promising. And regarding the influence of dynamic load balancing, we can see that it is quite dramatic, because the new implementation can be about 6 times faster as the current one in the typical range of data distribution in calculations that are usually run using CWIPI. So if you had here about 10% of the processes that actually handle a part of the coupling interface. We can see that in the new implementation, you do not, you have basically the same performance as if all the processes shared a part of the interface. And this is done using dynamic balancing for the geometric localization algorithm. And we expect to see an even greater acceleration for more complex examples using, for example, volume or high order coupling interfaces. And actually, the load balancing induces very little overhead compared to the costs of the whole computation. So I believe this is the way to go. We are also currently working on two new spatial interpolation method. So the first one allows to interpolate in a point cloud using a k nearest neighbors algorithm to find for each target point the k nearest source points. And from there, you can interpolate. By default, we use a least square interpolation. But again, the user will be able to use its own interpolation methods using callbacks. So if you want to use RBFs, for example, you just have to plug in your own function. And here, this algorithm also shows promising performance. So for example, for 2 point clouds of 100 million points each, if we seek the 5 nearest neighbors for each target point, this is done in less than 4 seconds on about 1,000 cores. So this is quite promising. And next, we are currently working on a method for conservative interpolation, which actually consists in intersecting both source and target meshes. So here we have an example of a 2D version. This version is quite stable now, and we are currently working in extending it to the generic surface case. And we intend also to develop a volume fully 3D version. And here are again 2 examples with both 3 million faces on both sides, or 300 million faces on both sides. And we can see that, again, load balancing does not induce a large overhead, and it enables a great improvement of performance. So finally, we expect to release a major new version in the mid of 2022. So I just said in the beginning that currently CWIPI suffers from 2 major constraints that are that the distribution of the couple codes on the processes is quite limited. So each of the intercommunicator of each couple codes cannot currently intersect. So each process can run at most 1 application. So future version will remove this constraint as shown on this little diagram. The partitions of the coupled applications will be able to be distributed arbitrarily. So we can have processes running both applications, and that will not cause a problem in the future implementation. So as I said, we intend to add the new spatial interpolation methods. So the improved localization algorithms, as well as the point cloud interpolation and the conservative interpolation method. Yes, in the next version, the control parameters will be synchronized using non-blocking one-sided communications using MPI RMA. Currently, this is another constraint. Each time you want to synchronize a global control parameter, you have to use blocking communication, and this causes a risk of MPI deadlock, as well as potentially degrading the performance. So in the next version, all the control parameters will be synchronized in a non-blocking way. So we intend also overall, we intend to make the communications asynchronous and non-blocking anytime, anywhere it's possible. And we also intend to go in this way. So for example, to allow time interpolation between applications that advance with different time steps. And so in this way, we also need to work in order to find very efficient ways of storing interpolated fields. And we also intend to develop a client-server mode directly within CWIPI without the need to using the open-palm coupler. So this way, we will be able to couple applications that typically do not use the same MPI implementation. And finally, we also plan to explore the hybridation between MPI and GPU to embrace the full potential of the heterogeneous architectures that are more and more common. And also we intend to generalize the use of one-sided communications using MPI RMA, again in order to pass the typical issues that are facing.
There is one question there, which in the question and answer, which says, how dense is the graph for a single exchange and how many point-to-point comms? Maybe you can just type the answer to that, and then I can open up to more general discussion.
Okay.
And we've only got 10 minutes of the official time, but we might just drift on a few minutes over. I don't know, Stephen, what you think?
Happy to drift.
Yeah, not too much. I don't want people to be to have a late finish, but we could maybe have 15 or 20 minutes.
Yeah, so we do have the technical capability to allow people to talk. So you'll just have to put your little virtual hand up if you want to actually say something with your voice rather than your words, and we can enable that.
So I suppose it's like, as we already sort of drew out earlier on, there are some general issues which I think all of these frameworks kind of say suffer from or need to address. Things like scalability, load balancing, how to get full utilization out of your compute resource whilst running multiple simulations. And I don't know if anyone wants to kick off. I mean, maybe from some of the other packages who haven't discussed that. Maybe Benjamin or Yvonne.
Well, actually, we touched a bit on that in the end of the presentation, where we're basically trying to get a balance between the memory, more complex structures like octrees, which seem to be interesting. I don't know. I actually have a question for Bastien. Is when you're using the redistribution in octree, are you using the octree that's in that was in FVM or another octree that you built differently?
Actually, no, we use a fully parallel octree, which is based on the paper written in, I believe I can send you the reference. It's written by Sundar et al. I believe it's a paper from 2008. So it's a, the octree is completely parallel. It's constructed from a bottom-up approach, and no, it's a bit different from the VM implementation.
Because the one from PLA, it's also the one I tested is also bottom-up and parallel, but probably slightly different. But the issue we have, so the approach is probably quite similar. And in that case, well, we see that it does require quite a bit of tuning to reduce memory, but it does improve scaling quite a bit. So that's one approach. And looking at other toolkits like DTK, they have KD trees, they have also bisection. So there are some other approaches that might be simpler, that might be a good balance that we haven't tested. Always that balance between complexity, memory use, not having too many parameters, because the parameter space we can search could be huge. So it is definitely something we see so far. Basically, running on a few thousand of processors, the performance impact of the coupling library, so it's probably seems similar for the other toolkits. The performance impact was not that bad that we really had to do something strong about it. And now we're reaching the point where we have to use things like octrees and go a bit further. But we do have ideas, the octree being one of the examples, but they do have trade-offs. Yeah, that's basically.
Yeah, we also have another implementation that uses bounding box tree, very similar to the one you described. But we found that the octree one performed a bit better. So in our applications, at least, there is much work to do left in this area.